The amplitude comparison can be done in a number of different ways, and therefore three types of amplitude comparators will be discussed now. The first type of amplitude comparator is integrating comparator, then instantaneous comparator, and the sampling comparator. There are various techniques to achieve the comparison of the inputs for an amplitude comparator, and in some of the techniques the inputs are rectified, while in some other methods only one of the inputs is rectified. And when only one input of signal is rectified, that rectifying quantity will be compared with the value of another input at the particular moment of the cycle. So there are different ways of doing the comparison. The first type of integrating comparator, and there are again classified as the circulating current type and opposed voltage type. The figure shows the circulating current type of amplitude comparator. The operating and the restraining quantity are rectified and then applied to a relay, which may be either slave relay or maybe a thyristor circuit. And in the figure we can see that there are two full wave rectifiers. One is for the operating quantity and another is for the restraining quantity. So rectifier bridge type of comparators are widely used for the realization of overcurrent and distance relay characteristics. The output of these bridges are applied to a DC polarized relay whose operation depends on the direction of current or voltage. Whenever the operating quantity exceeds the restraining quantity, the relay operates, as also shown from the characteristics, VI characteristics. The another type of integrating comparator is the opposed voltage type amplitude comparator, as shown in the figure. It works with the voltage input signals derived from the PTs. The operation depends on the average of difference of the rectified voltages V1 and V2, and if this difference is positive, then the relay operates. Another type of amplitude comparator is known as instantaneous comparator, where the instantaneous values of the inputs are compared after rectification. The instantaneous comparator is also subdivided into two types. First is the averaging type and another is the phase splitting type. Here we can see the averaging type of the instantaneous comparator. So this is a block diagram of averaging type instantaneous amplitude comparator. In this comparator, the restraining signal will be rectified and it will be smoothened completely in order to provide a level of restraint. This is then compared with the peak value of the operating signal, which may or may not be rectified. The tripping signal will be provided when the operating signal will exceed the level of the restraining signal. Hence, a level detector has been connected here, and this is basically comparing the AC or the unsmoothened rectified DC signal with a DC reference. For inputs below the reference or the DC level detector which is set, the output of the detector will be 0. The graph shows the V-shape of instantaneous amplitude comparator, and as seen from the output, it is seen that the tripping has been identified as the dashed red lines, and this is showing the region wherever the operating signal which is rectified is more than the restraining signal. Second type of instantaneous comparator is known as phase splitting type amplitude comparator, and in this type of comparator, single phase inputs are splitted into say three phases outputs and then rectified so that the output after rectification is smooth. Although smoothing can be done with filters, but these circuits introduces a delay which is not suitable for high speed relaying. This figure is showing us a phase splitting of inputs before rectification. The input is split into 6 components 60° apart so that the output after rectification is smoothened within 5%. As both the input signals to the relay are smoothened out before they are compared, a continuous output signal is obtained. The third type of amplitude comparator is sampling comparator. Sometimes it is convenient to get the required characteristics by comparing the magnitude of one input signal at a certain point on its wave against the rectified and smoothened value of the second signal. So in sampling comparators, one of the inputs will be rectified and it is compared with the other input at a particular moment. The instantaneous value of the other input is sampled at a particular desired moment. Such comparators are used to realize the reactance or the Moho relay characteristics. Reactance characteristics is one such case where the instantaneous value of the voltage at the moment of current zero is compared against the rectified and smoothened value of the current. If the current lags behind the voltage by an angle phi, then the value of the voltage at current zero is Vm sin phi, and the reactance relay will operate whenever x is less than k. That is, Z sin phi is less than k. Phase comparison can be made in a number of different ways. Some important techniques are vector product phase comparator and coincidence type phase comparator. In the vector product phase comparator, the output is proportional to the vector product of the AC input signal. Hall effect phase comparator and magnetoresistivity phase comparator falls under this category. The another type of important phase comparator is the coincidence type phase comparator, which will be discussed in this section. Phase comparison technique is the most widely used for all practical directional distance and differential relays. Considering two input sinusoidal signals S1 and S2, the period of coincidence of S1 and S2 will depend on the phase difference between these two inputs. Figure illustrates the coincidence of signals for different phase relationships. As shown in the figure A, S2 is shown lagging S1 by less than 90 degree. In the B, S2 is lagging S1 by 90 degree. In figure C, S2 is lagging S1 by more than 90 degree. So it can be seen that the period of coincidence is equal to the period of non-coincidence for a phase difference of plus minus 90 degree. And the period of coincidence is less than the period of non-coincidence and vice versa when the phase difference is less than plus minus 90 degree. Depending on the phase relation of the input signals, it is possible to design a circuit to give an output in yes or no form by measuring the period of coincidence. The period of coincidence of two signals with a phase difference equal to 180 minus theta. Different techniques are employed to measure the period of coincidence, which will be discussed in the next section. Various techniques have been developed to measure the period of coincidence. So first we'll be discussing the phase splitting type of phase comparator. In this technique, both the inputs are split into two components and shifted plus minus 45 degree from the original wave as shown in the figure. All the four components which are now available will be fed to the AND gate as shown in the figure B. The tripping will occur when all the four signals become simultaneously positive at any time during the cycle. An AND gate is used as a coincidence detector here, and the coincidence of all the four signals occur only when the phi is less than 90 degree. So the full range of operation is defined as phi lying between minus 90 to plus 90 degree. This technique is also known as the direct comparison technique. Shaded portion in the figure A is used to show positive values simultaneously, that is, the relay will trip only for phi less than 90, and when phi is equal to 90, relay does not trip. The second type of phase comparator is the integrating type phase comparator. Figure A shows the block diagram of integrating type phase comparator. The input signals are sinusoidal signals which are first converted into square waves and then are applied to the AND gate. AND gate acts as a coincidence detector, and the output of this AND gate is a chain of pulses as shown in the figure B. This is for phi less than 90, that is psi, which is period of coincidence is greater than 90 degree. The relay will provide a trip output, and the output will be then applied to an integrator. The output of integrator is shown in the figure C. This output is then applied to a level detector, which finally gives a trip signal. Figure D and E shows the output of the AND gate and the integrator respectively. This situation is for psi equal to 90 and is the limiting condition, and the relay may be said to operate at psi equal to 90 degree. The third type of phase comparator is known as time bias type phase comparator, and it is based on the block spike method. That is, in this method, one of the input is squared and the other input is turned into a spike, preferably at the instant of its peak value, as shown in the figure. The coincidence of the input signal will occur only for the phase difference lying between -90 to +90. So figure shows the schematic block diagram and the waveform. The output will be available for different phase differences as follows: with spike derived at peak value, with spike derived at zero value, and with the spike derived at any other instant. The figure shows a static instantaneous overcurrent relay. The block diagram of the static relay has been shown here. The input CT is called the auxiliary CT, which has the taps on the primary for selecting the required pickup current. The output of auxiliary CT is rectified and smoothened and applied to an overload level detector and a resistive capacitive RC timing circuit. When the voltage across the timing capacitor reaches to a critical value, then it will trigger the level detector. The output of the level detector is amplified as per the requirement and is sent to the tripping circuit. This operates the output device. The charging of capacitor in a timing circuit is achieved by the voltage which is derived from the CT current. This voltage is obtained across the nonlinear resistor by passing rectified current through it. The proper selection of the nonlinear resistor in the RC timing circuit allows to obtain the desired shape of time current characteristics of the static relay. Figure B shows the detailed circuit diagram of instantaneous static overcurrent relay. An auxiliary transformer gives the output voltage proportional to the fault current. The main circuit is protected from the voltage surges by using an R1 C1 circuit at the input. This is also called the surge protector. The output voltage from the transformer is then rectified and smoothened using capacitor filter C2. The level of this voltage is compared with the voltage level decided by Zener diode ZD1. This Zener limits the rectified voltage to a safe value, though the fault current is very high. Part of this voltage, as decided by the potentiometer P, is compared with the breakdown voltage of another Zener diode ZD2. When the rectified voltage is greater than voltage of ZD2, the transistor Q1 conducts. This increases the drop across R2, due to which Q2 conducts. This will energize the trip coil TC of the relay. When the trip coil opens, it develops high reverse voltage, also known as back EMF. To protect the transistor Q2 from such a high back EMF, a diode D is connected across the trip coil. With the help of potentiometer P, different pickup values can be obtained. The figure shows the circuit diagram of static inverse time overcurrent relay. Under normal conditions, the transistor Q1 gets biasing from the DC supply applied through the resistance R4 and P2 and conducts. Hence the capacitor C is short circuited. When the fault current exceeds the pickup value set up by the potentiometer P2 and the selector switch, then the transistor Q1 is off. The capacitor C starts charging through R3 and P1 by the voltage developed across R1. This charging time varies as per the severity of the fault. More severe is the fault, more will be the voltage developed across R1 and less is the time for charging capacitor C to a critical level. When the voltage across the capacitor reaches to a predetermined level set by the potentiometer P3, then the transistor Q3 conducts. This will energize the trip coil and hence the circuit breaker opens. The diode D protects the transistor from high reverse voltage. Thus, more is the fault current, less is the time required to operate relay, hence it is inverse time current relay.